Complex integration. Complex integration. When we are dealing with real functions, an integral of this type, for example, fx dx, fx is real function here, a, b, these are limits of integration. We know that in this case a, b, both are real numbers and they lie in this on this line, real line AB, and we are then from A to B we are integrating. This means we are actually calculating the area under fx curve between A and B. This graph shows the same, x here, fx here, and then A here, B here. These are limits of, and let this be in this be say fx. Then by this we mean total area under this curve from this area. And this is so simple because fx here is, that is the altitude or the height, and dx is a small say let us say length. So df into dA, fx dx is the area of this small rectangle. When we take all these, we divide this area into these small rectangles and then take the this integral, sum of them all, then we get this. This meaning of the integral was first given by Riemann, and hence it is called Riemannian integration. There is another type of integration, we call that Laubach integration. Spelling of this name is slightly different as compared to its pronunciation. This Laubach integration. In this integration, instead of dividing x-axis into infinitesimally small these pieces, infinitesimally small pieces, Laubach integration divides fx into infinitesimally small pieces. Now, anyhow, we don't have Laubach integration anywhere in our syllabus here, so we will confine ourselves to the well-known Riemannian integration. Now, leaving this thing aside, let's move ahead. See, when we have this integral, the path of integration is only a single path from A to B, two fixed points, and path of integration is this. You are dividing this for this piece dx belongs to the path. This here dx here is a representative of the path, and fx is of course function defined on this path. Now, important thing is that there is only one option for this integral. There is only one path. There is no second choice. And in most of the cases, what happens is that the value of the integral is path independent. It depends only on the only on the endpoints. For most of the, but not all, of course, there are certain conditions under which this happens, and most of the time those conditions are satisfied, hence this turns out to be path independent. So there being only one path, so this path, even we don't describe this, while for example taking this integral, we don't even care about this path. So because we have in our mind that this is the path, there can be no other choice, so there will be no confusion. So let us now move to complex integration. In complex integration, you have to switch from this one-dimensional path to two-dimensional plane, the complex plane. We have this real axis here and imaginary axis here. Every point in this plane has two coordinates. One is the coordinate given by real axis, the other is the coordinate given by this imaginary axis. So if you have two fixed points, say A and B, here A and B, they are not, these points are not, these are complex numbers. A is complex number, B is complex number. Now there can be infinite number of paths between them. You can integrate a function along this path, you can integrate a function along this path, you can integrate a function along this path. Had all the integrals here been path independent, if these integrals here, suppose for example I show you a complex integral. Now I have replaced x by z and dz. Remember that dz is the piece of this path. Now I have this from a to b, say for example. Now this integral, had this been path independent always, then we would not care about the path. Again, we would not care about the path perhaps. But there are many cases in complex integration where, and very common cases, where the integral along one path gives one value, integral along the other path gives another value, integral along the other path gives another value. This means that in complex integration, path is important. Same integral may give different values along different paths, so you just cannot ignore them. So with so many options available, so what we do, we when we speak of now the importance of path is so important in complex integration that when we say that find the value of this integral, this complex integral, find the value of this complex integral from say some number, say 3 plus 2i, a complex number, to 5 plus 6i. For example, when we say find the value of this integral from this point to this point, we say that the question is wrong. Why is question wrong? Because you have not specified, the questioner has not specified the path along which this integration is to be carried out. So when you find questions on complex integration, you find some questions like this. You find evaluate something like this, evaluate this, for example, this, evaluate this along, say, z equal to 2. For example, what this z equal to 2 means, mod z equal to 2, you know that z is equal to x plus iy. So mod z is simply that is equal to root x square plus y square. It is mod. If we take z square is equal to 4. It means that the value of z is fixed. It is fixed. Value of z is fixed. You have z square equal to 4. Value of this, mod z is fixed. That is 4. This also means we can say then this root square of this, that is x square plus y square, is equal to 4. But you are familiar with this equation. This equation is the equation of a circle with center, of course, at 0 0 0 0 center and radius equal to 2. So you are asking in your question, you are asking to integrate this along a particular path, along say a circular path of radius 2 centered at 0 0, of radius 2 centered at 0 0. This is the particular path along which you are carrying out this. So this is very important for us, to specify the path. Without a specific path, your question is incomplete. That is the importance of path now. Now, since path is important, then paths can be of a number of types. A path is usually called, we call it by a name that we call curve. In general, it will be a curve, in general, a two-dimensional curve. But if this curve can be, say, of two types, for example. It may be smooth, that means continuous at every point, or it may be say, for example, we can say something opposite, non-smooth. Now, it may be a curve which is not continuous at every point. If a curve is smooth, well and good, that is okay. But now smoothness can be of two types. Number one, you can have a curve, or we should better. Let us keep this smooth separate. So a curve like a smooth curve may be, for example, like this. This is a smooth curve. There is no break anywhere, or a say corner anywhere. So this is a smooth curve. Now, what about non-smooth curve? Something like this, for example. You may have some curve like this, and this. Look at this corner. Here it is discontinuous. And now there can be two types of these discontinuities. If a curve is discontinuous at all points, everywhere it is discontinuous, then that curve is a very complicated thing. And for integration, we would better avoid such a curve, because we won't be able to. Either the integration will become extremely difficult, or the integration may not be possible along such a curve. On the other hand, if you have a curve that consists of course, these discontinuities, but only finite in number. Like say, suppose you have a triangular path. This is a triangular path. This triangle has three discontinuities. Here, 1, 2, and 3. Rest of it is continuous. See, let's take this piece of the curve. This here I am talking about dealing with a closed curve, something like this. I'm dealing with a closed curve. Now this closed curve is not smooth like this. It's not smooth at every point. It has corners, and at each corner it is discontinuous. Now limit from this side and limit from this side will not be same. Now at this corner, for example, this finite, this is called, we say that our curve here, a closed curve is often called contour. There is some confusion regarding this nomenclature. Often we call, some people say that contour means only contour represents only closed curves which are either smooth, completely smooth, or piecewise smooth. That means smooth but in pieces. This piece is smooth, this piece is smooth, this piece is smooth. But some people differ. They say no. Contour is, yes, contour is, sorry. Some people say that contour is a smooth or piecewise smooth closed curve. Closed. Both of these are closed curves. Smooth or piecewise smooth. Whereas, if a curve is not closed, it is called curve but not contour. However, there are people who say that no, a contour is both. It refers to both closed as well as this open curve, but the curve should be. The only requirement of contour being qualifying as contour is that the curve should be either smooth, completely smooth, infinitely smooth, or the curve should be at least piecewise smooth. So anyhow, we will use contour in the sense of a closed curve, but the closed curve will be either of this type or of this type. That means either it will be totally smooth or it will be piecewise smooth. One more thing, the curves that we will be dealing with. Why closed curves? I will just come to that. Why closed curves? Why we need these closed curves? One more thing, that is the curve. Any curve can say, if a curve does not intersect itself, or we can say, if you call this is intersection here, for example, or something like, let this be an open curve, and if suppose this curve does not intersect itself like this, it does intersect here, it intersects itself. Now if it intersects itself, then it is not called simple. If it does not intersect itself, it is called simple. These are simple curves. Simple here, whereas this is not simple. something like this is, says it is simple because it does not intersect itself. But this is not simple because it intersects. We will take simple curves, that because that will make our integration quite simple. I'm sorry. Let's go back. And then, now, having said this much about these curves, importance of these curves in this complex integration, now let's turn to one of the most important the theorems of complex integration, that is called Cauchy's. I wonder this about this man, how much contribution he has made in the world of mathematics and physics. Cauchy's theorem, Cauchy's integral theorem. Integral theorem. The name will matter. Integral theorem. So, what is this Cauchy's integral theorem? This Cauchy's integral theorem is about a function. Say, suppose you have a certain region. This is a complex plane. In this complex plane, suppose a function, a complex function, fz is defined in a certain region. Not only defined, but it has certain, the region is simply connected. Now, this region is simply connected. Call this region, say D, domain D. In this region, fz, suppose this fz is analytic in this region. Within this region, this region is the region of analyticity. That means at every point of this region, this fz is analytic. Analytic means at every point it is not only differentiable at that point, but also differentiable within a neighborhood of that point. That analytic quality of fz is very important, as you will see. Suppose, and in this region where fz is analytic, there is a closed this curve, a contour, say of any shape. Let me take this contour C. Let me call it C. And we will make a convention. That's not a law, it is a convention. What it is? Our convention will tell us, by our convention, we will always traverse a curve in anti-clockwise direction, a closed curve in counterclockwise or anti-clockwise direction, which is here this direction. All curves, so that there is no confusion about this. And this direction of traverse matters a lot. It can turn this integral from positive to negative. Anyhow, let's go without going into these minor details right at this stage. We will understand all of them, every bit of it, but slowly and gradually. We have now this closed curve, and they're completely contained within this region. In this closed curve, and inside this closed curve, of course, our function fz is analytical everywhere inside this and on this as well. Both these are important. It is analytic on the C and inside the C. Then, if that is the property of this fz, then Cauchy's integral theorem tells us that a loop integral, that loop integral simply means closed line integral, fz dz 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 has these pieces of this dz along this curve C is 0. A remarkable result. Really a remarkable result. fz has to, if we fulfill certain conditions, then this will always be 0. Whatever be the, say, suppose for example, there is something so this frightening as, for example, z raised to 1 by 2 minus z cube plus z 6z into dz divided by something like z cube plus z square plus z plus 5 into yes, of course, dz. If if you ensure that this fz is continuous, it is analytic at every point of this curve, and at every point inside the curve in this region, then this will be 0. You need not even give a second thought to complexity of this, not at all. Provided you fulfill these conditions. What are the conditions? Let us first see what are the conditions. Let us be clear about this. The conditions that we need to fulfill or include: number one, that include that this closed curve, which this closed curve should be smooth. Once again I go back to this, and here is my curve. This is curve. It should be smooth. C, I will denote it by C. It should be smooth. You know that. Continuous at every point. It should be simply connected. You know that. It should be closed. Good. These three things. And then the function fz. Now we turn towards fz. The function fz must be analytic at every point on this curve and inside it. And it is inside it. Okay. Then integral this integral of this loop integral, closed integral. That means you have to start integration from a point and then have to come back to that point. This is called then loop. Line integral is then called loop integral. Now this loop integral will then be equal to 0. There is when Cauchy actually stated his theorem, this is his theorem. When he stated his theorem, he stated one more condition that this has to satisfy. That condition is that the first order derivative f dash z of this f should be continuous at every point on the curve and inside. But after 75 years after Cauchy's statement about this function, exactly around 75 years, there was a man, he was a mathematician. His name was perhaps Goursa, Gour, T is silent, so it is Goursa. He said that this is not needed to be stated in this as a condition for this to be true. So there are two versions of Cauchy's integral theorem. One version is that the function should only this f dash z, the first order derivative should be continuous. That is the first. That is called that is the original statement of Cauchy's theorem. And the second statement is simply that on fz should be continuous at every point. It should be analytic, at every point on the closed curve and at all points inside it. No need to state this condition. However, if you do not state this condition, then that is called stronger form of Cauchy's theorem. If you state this, that is called, of course, the ordinary form or the normal form of Cauchy's this theorem. So it is up to us whether we carry this burden with us or not. Otherwise, we can also just take this as the necessary condition that fz should be analytic on this curve and inside at every point inside it. Having said that, now the question is, how is it that this integral is 0 irrespective of the complexity of this integral, this function fz, integral function fz? Let us see how that is possible. Let us see. We start with this. We know that fz is a complex function. It has two parts, u plus iv. You know, u is its real part, v is its this imaginary part, as well as z is equal to x plus iy. We are working in a plane. Z is equal to x plus iy. Dz will simply be equal to dx plus I dy. Now bring this integral here. Let us write I for this integral. Integral I C fz dz can be written as, now as per our this statement, it can be written as closed integral. This circle on the integral is closed. Physics and engineering students are aware of this because of this Gauss's law of electrostatics. Now this fz is u plus iv into this dz. This dz, for example, dz is dx plus I dy. Okay. Now, if I multiply these, I obtain this. I is equal to integral c to closed curve c back to this. I have u multiply now this u dx plus I u dy plus I u dy, then iv dx plus iv dx plus again I have iv dx. I have completed. Now I into I, that is minus 1 v dy minus v dy. Just do one thing: separate real and imaginary parts of this expression. We have this situation sorry, just a minute. Okay, now you have u, so this is first of all integral u dx plus then this is minus v dy. Okay, plus then again I is common here, I u dy plus v dx. What I am going to do now, I will split this integral into two integrals, one for the real part, another for this imaginary part. I have c, then u dx minus v dy plus integral c I u dy plus v dx. Okay, then this is I here. Now I will be now using Green's theorem here for this and for this. Now back to Green's theorem. Let us write equation number 1 to this. We have Green's theorem is here. You have line integral of loop integral of p dx plus q dy equal to according to Green's theorem that I have actually taught in my last lecture. This I will not go back to that. I assume that you know that, and it will be better if you have a first a review of that and then come to this topic. P dx plus q dy is equal to this. Green's theorem converts this line integral into a surface integral. There is a convention. Some people show surface integral by two integrals because surface is a two-dimensional thing. Some people show it like this, or some people show just by one, but keep a s here. That means it is surface integral, not line integral. Let us go with this common convention, and we show it by a double integral. And this double integral, the surface, is called the domain. This refers to the domain of the function. That means this in which the function is defined. Okay, then you have this is then see what happens is that you have this equal to d del q by del x minus then we have del q by this is del q by del x minus del p by del y. This is our dx and dy. This is our Green's theorem. So with this, we will be using this theorem first for this, then next for this. But before that, let me do one thing. Let me just 1 minute. I will write these two results on my paper here, and after writing them, I will go. First result is the integral is equal to integral c. I mean this. I mean what I am talking about is this equation. This I integral u dx minus v dy. You can also note at your place if you want, plus I integral, then we have c, integral c, then u dy plus v dx 1, and then Green's theorem written below it, that is p dx plus q dy is equal to this double integral over the region d dq del q by del x, partial derivative del p by del y, and area, since it is this we are dealing here with area, this dx dy. Okay, dx dy. Now I will turn to the other page. I have actually written here dx. That is wrong. It is okay. Actually, it is not writing here because being at the end. So I will go to the next page. So here is the next page. So I have now. I will write here. I have already written it. I have the first equation is I is equal to integral closed integral or loop integral u dx minus v dy into plus then I have sorry, what happened? I have okay, I have this is my last page. Now I go to this. I don't know what happened actually. Anyhow, I is equal to then integral u into c u d x u dx minus v dy plus again integral c, then you have u dy plus v dx okay, into dx dy. Now I'm going to apply Green's theorem to this first and then to this. And Green's theorem is, let me keep it written here, that is integral c p dx plus q dy is equal to this double integral and we have in that dq by dx minus dp by dy. You must have felt that this is basically curl a component of curl, and we have then dx dy. So substituting now using this for first part, then I will be equal to, we will use it with patience. First identify that in place of p, instead of p you have u here, and then in place of q you have minus v here. So if I now write this double integral for it, this double integral is not closed. The surface itself is not, it is bounded but not closed. Now d, you have dq, q is this is q, and this is p. Now dq but minus dq, you know why? Because it is minus v, dq by del q by del x, sorry, minus del p by del y, Now p is u, that means del u by del y, del u, it is like this. Del u by, this is del u by del y, yes, del u by del y. So it is one part of this. That's one part. Into d, of course, into dx dy. Dx dy. Sorry, dx dy. The other part is d, that is for this. For this. Now you have I here first. Then u dy. So p is again u here. P is u, p was u here, p is u here. And then, but things have changed in the sense that you now have dy here. We should have written it dx first and then dy. Anyhow, we have done it. Now, it would be better if we write here, for this case, we write this first, this first equation, dx equation. Otherwise, it will create a confusion. Not only confusion, it will lead to a mistake by you. So please bring this to the first position and this to the second. Anyhow, we will take it now like as we did here. We have here first dq will be this, that will be del u by del x minus del u by not del x, sorry, it will be del u by del y, del u by del y. Was it del? No, it is v dx. So it will be del u by del x. Sorry, yes, this is the first. It will be del u by del x as it was here, del dx and del x. Okay, it is okay. Now del u by del x minus del p by, now you have q is here equal to u. Q is u, that is why I have got this. Now p is here, this v. So it will be minus, not minus, yes, minus del v by del y, then del x del y. So dear, you should be a little bit careful. I think we should have first arranged it, kept this here and this. Now I believe that you can do it yourself, and so I have moved ahead. See now. Sorry, it is dq. Q in the first case was, this q was v, so it is dv del v by del x. Del v by del x. Now dear, you know that by CR equations, so far as CR equations are concerned, I will remove this Green's theorem here, and in place of that I will write CR equations. Now according to CR equations, ux is equal to vy, number one. Number two, uy is equal to minus vx, or writing explicitly in terms of these derivatives, then it is del u by del x is equal to del v by del y, and then this del u by del y is equal to del minus del v by del x, del v by del x. So suppose you have del v by del x, del v by del x, del v by del x is here, minus del v by del x is equal to plus del u by del y. So if you replace it by its value, what is its value? Its value is del u by del y, del u by del y, del u by del y. Replace it. What you are left with then? Del u by del y minus del u by del y. So 0. The first part of the integral is gone. Now come to the second part. You have del u by del x minus del v by del y. Again replace del v by del y. Del v by del y is here. Del v by del y is del u by del x. So write here del u by del x. Once you write here del u by del x, you now have del u by del x minus del u by del x, and that it vanishes. So what you are left with? I equal to 0. This Morse result, I equal to 0. Oh gosh, you can see what a result it is. I equal to 0. But what was I? I was this integral fz dz loop integral say is equal to 0, provided this fz satisfies certain conditions and C satisfies certain conditions. Conditions to be satisfied by fz are it should be analytic at every point of this curve and inside the curve. If it is not, suppose it is not, we will take that case, suppose it's not analytic at some point, at least one point inside it, then this will not come out to be 0. We will take that is what is called Cauchy's integral formula. In Cauchy's integral formula, we deal with functions which are not analytic at one point. We don't deal with functions that are analytic at 2 points, that are not analytic at 2 points or 3 points or 4 points. We just we remain confined to functions which are not non-analytic. At say, non-analytic functions are called singular functions. If a function is not analytic at a point, it is then said to be singular function. In Cauchy's integral theorem, the function that we are dealing with has no singularity on C or within C. Remember this thing. If it has, it will not come out to be 0. You need a proof, you will be provided with a proof. Let us move ahead and you will see. Even a single this singularity destroys this. The value does not come out to be 0 then. It is only for those these curves which only for those functions which are neither singular at any point on the curve or inside the curve. If now we have such functions which are singular, those are of two types. Number one, functions which are singular at just one point. If a function is singular at one point, I once again tell you that singularity means that the function is not analytic at that point. Now, if a function is singular at one point, then that is taken care of by Cauchy's integral formula. Provided that singularity is of a particular type called pole. We will discuss all of them gradually, slowly, gently. So, if a function has if it has single singularity, then that is dealt by Cauchy's integral formula. Then, if it has multiple singularities, then it is taken care by residue theorem. That will be one of our important results of complex integration, residue theorem. So we have three cases. Function not singular, then it is taken care of by Cauchy's integral theorem. Function having one singularity, that too, of course, I need to qualify my statements a little bit, but often what happens is that when you start with rough ideas, you can then later on chisel them and fine-tune them and then bring back rigor. So that your mind is already ready for that. A big picture is this, that if a function is not singular, then it is taken care of by Cauchy's integral theorem. If it has one singularity, enclosed of course within this, then it is taken care of by Cauchy's integral formula. If it has multiple singularities, then we use this residual theorem. After finishing these two, we will be left only with Taylor's and Lorentz series. That will be the end of this unit. Now let us go back before going to these Cauchy's integral formula and residue theorem. Before going to them, we will first do one more thing. That is, we will take up some problems, especially an important integral that I will be using here in this Cauchy's integral formula, and then we will take this and this. Okay, but that will be in our next video. Thank you.